today's lesson. All right, talking about casting and the ranges of variables. So I'll recap very quickly about when we do a calculation using an integer and a double. Anytime we do one of those calculations, the result is always going to default to a double value in order to preserve accuracy. So if I have my double first and my int second, first is 4.0, second is 2, the integer. If I print first divided by second, my result is going to be 2.0 in order to save that decimal place. But what if I want the result to be an integer? That is where a process called typecasting is going to come in. Typecasting is when we turn a value of one type into a different type. And it's done by putting the type that we want to turn something into in between parentheses in front of the value that we want to transform. So here I have the double value 5.6, and I want to save it into the integer x. So I'm going to use the int typecast. So I have int inside of parentheses in front of the value I want to transform. So the value that I store in x here is just going to be 5, because I'm going to truncate those decimal places when I do that conversion. I'm just going to get rid of those decimal places. They don't exist anymore. Does the very basic premise of how typecasting works make sense? Is that fundamental idea? Cool. All right. So what do you think will happen if I try to save the value of a double variable into an int variable? So if I have my double x equaling 5.5, and I say y equals x, what do you think will be saved into y? All right, I have a guess for 5. Any other guesses as to what would happen?
There would be an error.
There'd be an error. All right. Well, your guess of an error is correct. So the error that we get is, it says incompatible types, possible lossy conversion from double to int. So what that means is Java is preventing us from accidentally losing data in this assignment, because we can't just save a double value into an integer without losing the values after our decimal place. Java wants to make sure that we don't accidentally lose any decimal places. The way we can fix this is by putting a typecast to int in front of our variable, because when we do it this way, Java knows that we are purposefully transforming a double value into an integer value. So any loss of data here is intentional. Java will prevent us from accidentally losing data by doing this. But if we tell Java, hey, I know I'm losing data and I'm okay with that, Java is totally fine with it. So if we have a double that we want to save into an int, we can typecast that variable or value as an int and then save it into that integer value or variable. Does that make sense why we need to typecast for this scenario? Cool. All
Mr.
right.
Mac?
Yes.
Can we typecast like an integer as a string to print it on the same line as a, so we don't have to use multiple print functions?
So, fun fact is Java actually has the ability to concatenate an integer to a string if you're doing a print. which is very convenient. So I could say my system dot out dot print hi plus x, and let's say int x equals 7. This should work. I will run it and test it for us just to confirm, but this should work when we are running our code. And this should let us kind of cut down the number of prints we're using, because it lets us extend one print into printing multiple things all at once. So, good question. And the answer is, we actually don't need to typecast in that scenario. At least I don't think we do. I'm pretty sure we don't. I will confirm when I test it. So, if I save an integer value into a double, this will work just fine because there's no accuracy being lost. Actually, there's accuracy being added. And Java is totally okay with that. We can add accuracy all we want. We just can't accidentally lose it. So if I say x equals 12, double y equals x, y is going to equal 12.0. We're going to add that decimal place and just kind of save it. And this process is called implicit casting, where Java is automatically just going to transform that integer value into a double. We don't have to do anything about it. It'll just work. So going back to division and the integer double kind of problem that we had, if I have an int dollars equals 100, int num people equals 40, and I have double dollars per person equals dollars divided by num people, what do we think will be stored in my variable dollars per person?
$2.5.
All right, we have a guess for 2.5. Any other potential guesses? Do we all agree that 2.5 is probably the right answer? Well, the correct answer is actually 2.0, because when I perform this division, both of the values that I'm dividing are still integers. So only after the division has happened and the decimal has been lost does that implicit cast from int to double actually occur. So if I want to prevent this error from happening, from that loss of data, what I can do is I need to make sure that one of my values in my calculation is a double. So I can typecast one of the two integers to a double in order to actually get the value I want. So I can typecast as a double, or I could multiply either one of these by 1.0, because anytime I do a calculation with an int and a double, the result will be a double. So if I multiply dollars by 1.0, then the result will be whatever number dollars was as a double. So there's a couple of different ways to approach it. First, we have our typecast. We can also multiply by 1.0. A variety of different scenarios we could do. And so this will give us the value we were expecting, 2.5. So does that solution or pair of solutions for integer division make sense, how it works and why we need it? All right. If I want to round instead of just truncating when I typecast from a double value to an integer value, I can add 0.5 to the value as I'm typecasting. So if I say double x equals 2, and I say int y is int of x plus 0.5, and x is 2.8, y is int of x plus 0.5, what does 2 round to? What is the nearest integer to 2?
2.
It's 2, absolutely correct. And what's the nearest integer to 2.8? It is 3, correct. So 2 plus 0.5 is 2.5. So when I truncate that decimal, I get that value 2 once again. 2.8 plus 0.5 is 3.2. So when I truncate my decimal again, now I have gone up to the next integer, so my value in y is going to be 3 instead of 2. And I can also do that same rounding process with negative double values. I just need to subtract 0.5 instead of adding it. So if I have negative 2 and I subtract 0.5, I get negative 2.5. So when I truncate my decimal, I still get negative 2. And negative 2.8 minus 0.5, negative 3.2. So truncating the decimal gives me negative 3. Does the process for rounding make sense? Is that useful? I think it's useful, potentially. Cool. Rounding? Cool. All right. Our last topic for today is numerical ranges, and specifically integer ranges. As we work with numbers in our Java code more, it's important for us to know the range of available values that an int can take. So if we think back to our primitive versus reference lesson a few classes back, all primitive data, which is going to include int and double values, is stored in the computer as binary. So here's the slide that we had before. I had my character x equals the letter A. In my head, the box for my variable x stores that letter A. But in the computer, my box for x is going to store a bunch of ones and zeros. And that is the binary value that corresponds to the letter A in my computer. Now, if I want to store an integer, here's how storing an integer looks. If I have my int x is 65, in my head, I think x is just storing 65. But in the computer, this is all of the memory that is allocated to that variable x. In this table, each cell here is referred to as a bit, with each row of 8 bits being called 1 byte. As we saw on this slide, a char or character value takes up 8 bits of storage, while an int is allowed 32 bits of storage. So, like I said, a Java gets 32 bits. Each bit has 2 potential values. It can either equal 0 or it can equal 1. And those are the only 2 choices for any given cell. We can use this info to find out how many total numbers we can store in a given int. Because if I put 2 to the 32nd power, I'm saying this is the total number of values possible to be stored in that space. So the number of different values I can store is 4,294,967,296. That is my total number of different integer values that can be stored in an integer typed value, or integer typed variable. Does it make sense why we are constrained like that? Yes, no.
Yeah. Yes.
Yeah. All right. So since we can store positive and negative numbers in integers, we need to divide that total number of values in half. So half of those numbers can be negative, half of those numbers can be positive. So our full range of integer values, our smallest integer value we can store is negative 2,147,483,648. And the biggest one is 2.1 billion. And the positive number is odd because we have 0 right in the middle, which kind of offsets our even numbers. So this is the full range of integer values. And for most of our programs, we're not going to like hit those limits, but those are the upper and lower limits. Yes, Owen?
If you went above or below that limit, would it just say, would it just like keep adding numbers?
I am about to talk about that.
Okay.
So, but good question. So, funnily enough, Java already has these values pre-programmed in. We can use integer with a capital I and fully spelled out .min value and integer.max value to reference those upper and lower bounds. We can also save those values into variables to use for ourselves. So what do we think would happen if I set my variable min to equal integer.min value, and then I say min minus minus? I'm at the smallest value, and then I'm going to subtract 1. What do we think will be stored in min? Keep in mind that our smallest value is this number. What do we think?
Maybe it would like loop back around.
Maybe it'll loop back around. Could it also possibly give us an error? Maybe. And the correct answer is, your guess was right. It will loop back around to the biggest number. This process is called overflow. Due to the storage restraint that we have, the values are going to loop back around from the smallest to the biggest end. So if you exceed a bound in either direction, the value is going to reset back to the other end. So essentially we have a 4 billion number long loop that we can store. All right, what do we think will happen here if I say my min equals my minimum value for an integer, and then I add my minimum value to my min variable? What is min going to store? We know that overflow exists. What do we think is going to exist, or no, the number is going to be here?
0.
0, correct. Because when I add a negative number, I'm essentially subtracting that value. So I'm subtracting from my huge negative number. It takes 1 to hit the overflow, and then we have this much left over, so that gets us all the way down to 0. So that is how overflow works. That is the limit on our numbers that we can store within an int. Cool. Very cool. All right. So let's test. Actually, this is not going to test anything yet. We want to print All right, so I'm getting two integers, I'm getting a string, and then we're going to print all of it on one line. Let's just test that this works. I think it will. Just double confirming. Yes. In Java, if you concatenate a string with an integer, it will do that same process of implicit casting. It will implicitly cast this integer value to a string and perform that concatenation. And it'll work just fine. So this will save us some lines of code now because we don't have to have all of our outputs be on separate lines. We can print all of the stuff all at once. Any other lingering questions about typecasting or integer overflow? All right. Then I will stop our recording.